detail. Batteries, we've heard about that. These are sort of the primary batteries. These are the one-shots, the alkaline batteries. And we know a lot about those, and we use them every day. We use them, and we burn them, and we throw them out. And then there's the rechargeable batteries. None of these, as we saw, none of these are yet even close to being something which I would argue we would immediately adopt as something we're going to throw in a car. That's why there's all these discussions, and that's why there isn't a certain winner yet, is because none of these really answer the problem. How do I compete with gasoline really in the end? So, and I'll show you a picture where, battery really takes up a half the car. That's not really an acceptable solution yet. And I'll just remind you as we go through this that, these are what we've heard again. Energy, power, and efficiency we talk about, but you cannot forget about, of course, cost, life, battery life, and safety. And this is a very simple slide with a huge amount behind it, that any system you choose, as we heard in the previous talk, you can choose any system, and there's a very complex interplay between whether energy density and power and, for example, life. And there's trade-offs, and it's a complex world. It's a non-trivial complex world. So that's my main point there. So let me talk a little bit about energy storage and batteries and some programs that we're exploiting recently. But let me repeat what the value of doing this is, period. And I think sometimes we forget this. If we could fully electrify the U.S. transportation system, this is just a Gedanken experiment, if you like, but if you could remove all cars that are burning gasoline today and replace them with batteries that are charged in the wall, right? So you're now going from a decentralized gasoline to centralized power plants, whatever they are. And this, by the way, these calculations we did, but also done at PNNL and other places, but they're based on not changing the mix of power plants. So, if you ramp up nuclear or ramp up solar, it's even better. But if you just stick with the current mix and you go from a car that burns petroleum and produces CO2 and burns, gas, you actually get these numbers. So you could, first of all, this is a well-known number. About a third of the consumption of oil is in our automobiles, light trucks and automobiles, light-duty trucks and automobiles. We cut those. And by doing that, we actually wheel well to wheels. So what I mean by that, this is a real calculation done from actually pulling oil out of the Gulf and actually processing it and putting it into your automobile, pumping it at the station, delivering it to the station. Every bit of the carbon produced for that gallon of gas, you reduce the carbon footprint by 25%. And so those are pretty good numbers. So it's a laudable goal. What we need, I'll keep saying this, is we need a dramatic increase in energy density to really make that possible. And we can live with 40-mile cars. I'm not saying we can't. But to really make this, penetrate the market, we believe you have to be well above a couple hundred miles for a single charge. These are just two pictures. This is actually, I believe, now we don't know, this is a stock photo. Many of you have probably seen it before. I think this is the Prius battery, but I'm not 100% sure. This is actually an automobile that we did some time ago, a plug-in hybrid electric. It's a GM car. It was an internal combustion car. We ripped it apart and we replaced it with a motor and we put a battery in. So this just gives you an idea of the scale. This is about a 10-mile vehicle that we drive around the grounds at Argonne. But look at the scale. I mean, it just gives you a sense of a real battery. So this is something we built. We work closely with GM, or we did work closely with GM. This was an interesting story I'll go into some other time. We collaborate closely with a lot of the auto companies. And this is just a car we built, and you just get a sense, right? I mean, you can get a sense of the scale of what you're dealing with. And so pound for pound or kilogram for kilogram, we're still not in the ballpark yet. So let me talk a little bit about our program and try to relate this back to what the challenges are. We've been doing energy storage at the lab. Actually, the person who works at the lab, who's really started this, is Mike Thackeray. And I don't know, Mike, if you know Mike. Mike was with John Goodenough down in Texas, who originally was the original guy who discovered the whole lithium, the concept of using lithium as a way to do energy storage. So we hired Mike, and now Mike works with us. And so he's been an important part in this whole program. I give him a lot of credit for a lot of things I'm about to tell you. At the lab, we do electrical energy storage, which I'll talk about, which focuses on things like batteries, some amount of grid storage, but mostly on batteries for transportation. But we also have a growing program trying to prototype and manufacture. And the only reason I mention this is I'm hoping there's industrial people and manufacturing people in the audience, because we are very interested in thinking about how to fill this gap between making a single cell and actually trying to ramp that or scale that and demonstrate its manufacturability, because there's a huge difference between making a cell on a bench in a laboratory and actually having something which you can really manufacture. So we work on that. In fact, this is a plant we helped set up for BASF to scale some materials that they license from us. But we do a lot of that. We have some work in stationary grid, which I won't talk about it. But the thing I want to emphasize is that when we think about storage, we also are very, very focused on energy transportation systems. So this is a dynamometer, which allows us to test new concepts. Once we design a battery, we can actually stick it on an automobile and test the concepts and efficiency. We also test cars. We test Priuses. We test, we test Ford cars. But we get to test new concepts. So this is just an experimental drivetrain, where we have motors. You can put a combustion engine on this, but you can also put a electric motor on it. So we can actually test the battery, and this is just a prismatic battery, just a rectangular battery that gets used in a car. So we can do all that kind of stuff. So let me come back to the same figure that's been shown a few times. This is just a different version of the same Ragone plot to reemphasize this trade-off between range and acceleration in these batteries that we have, right? So it's always going to be this. It's the same plot you showed, but it's flipped. But I want to make a few points on this, right? So one is the same point that was made before, which is that you clearly trade off when you want to go to, you can go to the high energy density, but then you don't have the same specific power, right? And so that's the trade-off. The red line here is sort of the state of the art today in lithium batteries. It gets you to the, if you will, the plug-in hybrid electric end-of-life 10-mile vehicle. So that's good. We're making a lot of progress. This line shows the best we can do today, but remember the internal combustion engine still sits way up here in terms of being able to deliver both energy and power. Now, as Americans, we really care about power. Probably Italians care about power, but not many other people do. But there is a trade-off. You can't give entirely up on power before you. So you can't just make a car that goes 100 miles with zero power. You can't do that. It's not just about acceleration. There's one other thing I wanted to make a point, because all the points were made on this plot before. On the Ragone plot here, you'll see there are these dotted lines that go up horizontally. These are actually very interesting, and they show, if you will, a discharge or a charge time. And so when we talk about a battery, we also have to be talking about how fast can you charge the thing. And so these show that when you want to get to a few seconds in charge time, or even a few minutes in charge time, like here, you're giving up. You gain power. It's like a flywheel. You gain power because you can deliver it fast, but you're at the same time you're giving up charge time or discharge time. So it's a direct trade-off. So if and this is a challenge. This is the systems challenge, the materials challenge, is that once I get to these very, very high energy, specific energy or energy density batteries, I'm taking a lot longer to charge them. So, so this is again a challenge, right? And this is the same challenge we heard about this morning. And always a caveat when you're thinking about materials. So I apologize. I am a physicist. So I'm going to take a few minutes to remind you how battery works. And we kind of heard this, but I do want to do this mostly because it points out what the fundamental challenges are in materials. We heard a lot of really nice discussion about what the high-level problems and the high-level challenges in systems and power electronics, controlling life cycle, et cetera. I just wanted to remind you what some of the fundamental materials challenges are, because that's what we work a lot on. This is a battery. You have a cathode, right, which in principle stores lots of lithium ions or some kind of ion. And then you have an anode. When you charge this thing, you basically take lithium from the cathode and drive them toward the anode. And this is just two example materials. An easy material to use for an anode is graphite, because graphite is easy to intercalate lithium. Small atom, it goes into graphite very easily, so you can load it up, and it retains its integrity as graphite. And then you've charged it up, and then you discharge it by plugging it into some kind of load, and the electrons flow one way, and the ions flow back the other way, right? So that's a battery, right? And that's how you get the energy out of the battery. You stored it by storing this electrical potential across these two cathodes. There are two major challenges. There are many, many challenges here. You heard about the electrolytes being very, very volatile. So the electrolytes are volatile. The material actually can be volatile. And so what's very, very, very important in a battery is controlling the interface between the electrode, the anode, and the electrolyte, and the cathode and the electrolyte. It's that where a lot of the explosions we heard about before, a lot of the safety issues happen right at that interface. When something runs away, you oxidize, something happens, chemistry happens. So we spend a lot of time worrying about how to treat that interface, either by pre-treating it, or very often when you first start a battery, when you first have a cold battery, it's never been charged before, you don't even have that protective layer. It actually is through chemistries that we don't fully understand that you develop a layer, a protective layer on that interface, okay? So that's one of the first challenges. So we worry a lot about that, and I'll talk about that in the next few minutes. The other thing that's very, very challenging from a materials point of view is that you take a material like this. So the material that I'm sort of depicting here, cartoon here, is a lithium transition metal oxide. okay? Lithium transition metal oxides. It's not, details don't matter. But if I start pulling lithium out of that material, it's no longer stable. So at both ends of that phase diagram, what we physicists call it, lithium rich and lithium poor, I do have two totally different materials that may have nothing to do with each other, and it turns out most often, at one end of that phase diagram or not, that material is not stable. So that cathode material just dissolves itself. I mean, eventually it just falls apart. And so that's another challenge, is making a material that has a large capacity for lithium, a source of lithium, but at the same time is stable at both ends of the spectrum. And I'll show you some of the things we're doing, again, not to emphasize the details of the materials, but more to say that these are the challenges that we work on. I want to highlight again the solid electric, SEI we call it, solid electrolyte interface is very, very important for us. So let me talk a little bit about that. Again, details. I'm not going to go into the details. This is a material. So I lied a little bit here. I'm showing a single chunk of material. It's a little bit hard to get lithium in and out of a solid chunk of material. So in the end, the materials that we use tend to be very fine grains, almost very fine powders, or you've heard of nanomaterials. So we use nanomaterials. And the reason we use nanomaterials is twofold. One is when I have little chunks of material like this, I can get lithium in and out easier because the boundaries are there. Pull the lithium out. Also, it turns out that little pieces of material are much more stable against large changes in composition. So I get this material. It actually works really nicely. And if you look carefully at this, this is an electron microscope image. You see a lot of goo on the surface. That goo is that protective layer that we put into this. And the only point I want to make of this is one of the things that's really important when you innovate new materials, and this is just to add to the points already made, is you can look before and after and see that the material is fallen apart. You can look before and after and see that something has changed, but you don't really know what's changed until you can actually go in and subtly probe that interface. So one of the things we do at the national labs, this is a synchrotron experiment, and I don't want to get into detail there. This is taking a huge accelerator, using the X-rays from that accelerator. And what you see here, so this is a battery as it sits on a shelf. So you charge a battery, right, and you let it sit, and you just watch what happens. So you would think if you just charge a battery and let it sit, it'd be fine. But it turns out you charge a battery, and it turns out that it falls apart on its own if you're not careful, if you don't have the right materials in there. So what you're seeing here, and the details again aren't important, is you start with this purple curve, which is a good battery. You can charge it to 100%, right? PF stands for power fade. So as you go to larger percentages, the power is fading. So this is, remember the capacity, if you call it whatever the kilowatt hours are, the capacity. You can actually watch that power fade, but from a chemical point of view. This is telling you about the chemistry at that interface. So this is the kind of thing that you have to be able to do if you want to break the barriers from these factors of 20% to factors of 2 or 3 that we do every day. And I just wanted to show that. That somehow got moved. So here's a material that we innovated, and I won't go into details again, but these are the kinds of lithium materials, and it's not just, it's clever materials engineering that gets you the solutions in these electrodes. Also clever chemistry when you talk about the electrolyte. What we've done in lithium manganese oxide, which is totally inert. It turns out the lithium is too strongly bonded in this material to move around. But it also means it's inert to oxidation. If we combine that with another material that does have a lot of lithium mobility and make those nanoparticles and make them stick together, we can actually make a much better material. And this is just the output of that. So this is just the theoretical. So I'm showing this a little bit to you to show you that you can do the material science, you can do the materials engineering, and you can actually dramatically enhance performance. So we learned about this interfaces, we learned about how to get lithium in and out of materials, we picked some clever materials, and then we come out with a material that's within a few percent of 10% of the theoretical limit. So just by doing the basic science on that material, you can actually learn a lot, and you can come back. And this material now, by the way, is licensed to 3M, BASF, Japanese company, Toda, because it basically just has about a factor of 2 over the previous cobalt-based lithium compounds. Yes?
This goo surface that you're talking about, is that in effect a kind of slow-moving fluid through which things are able to move?
So it's a very good question. So we don't exactly know what it is. It's certainly not a fluid. It's a solid. I mean, these are fairly solid interfaces. The key to that goo is that the lithium has to diffuse through it one way, but the electrons can't go back through. And the electrolyte has to protect the it has to protect the cathode or the anode from the electrolyte. And so the goo is, if you will, transparent at some level to the lithium ions. They can get through it, but it also won't allow the electrolyte material to pass back in and corrode the electrodes.